Data Skeptic is the official podcast of dataskeptic.com, bringing you stories, interviews, and mini episodes on topics in data science, machine learning, statistics, and artificial intelligence.
Pranav Rajpurkar received his BS degree in computer science from Stanford University in 2015. Currently, he is a PhD candidate in Stanford's machine learning group. His research focuses on developing machine learning algorithms and applying AI solutions to high-impact problems. Pranav, welcome to Data Skeptic.
Hi, thanks for having me, Kyle.
So I read your recent paper, Cardiologist-Level Arrhythmia Detection with Convolutional Neural Networks. To get started, could you give me an overview of what you and your co-authors worked on?
So we investigated the task of arrhythmia detection from ECG signals.
What is arrhythmia exactly?
So arrhythmia refers to the irregular beating of the heart. Around 3 million people in the US are affected every year by arrhythmias. The most common serious arrhythmia, atrial fibrillation, affects about 34 million people in the world. So most people know someone who has atrial fibrillation.
And is the ECG, the electrocardiogram, is that the primary tool for trying to get some diagnostics to tell people if they have these issues?
It's the first tool that doctors use. One thing that's great about the ECG is that it's very non-invasive. There's no pain involved. It just measures the electrical activity of the heart, and using that electrical activity, the ECG recording, doctors are able to make inferences on what kind of arrhythmias the patient might have.
Am I correct in saying that the sort of stereotypical machine you see on a TV show in a doctor's office with the beep, beep, beeps, is that the ECG?
Yeah, you can see the ECG being shown in real time with the heart rate as well.
And then to understand the data, obviously it's a time series. Am I correct if I read that as a two-dimensional thing, that at every sample there's some magnitude, or is it more complex of a signal?
Yeah, that's right. So we're working with single lead electrocardiograms. Normally, diagnosis in the hospital, it's done with a 12-lead ECGs. The doctor will place electrodes at different places on the body and then be able to get a lot of different perspectives into the 3D electrical activity in the heart. And getting a single lead ECG, that means 2 electrodes, is like getting one perspective. We're looking at a more difficult problem than is normally looked at in the hospital setting, where in our case, we only have a single lead ECG. It's only one perspective. You can think about it as having one camera angle into the heart and being able to make diagnosis out of that.
So obviously we'll get into more details about your work and the accuracy levels you guys achieved. Do you see that as a future area of exploration? Will a multi-electrode system provide more information, empowering your algorithms to make smarter predictions?
Definitely. Many heart diseases, including myocardial infarctions, AV block, ventricular tachycardia, atrial fibrillation, they can all be diagnosed from ECG signals. Some of them are harder to diagnose with single lead, but are easier to diagnose with multiple leads. So that's definitely an area where more work is very useful. The benefit of having a single lead ECG, especially in our case, is that it's ambulatory. We just have one device that people stick on their chest, and it monitors the ECG continuously. Of course, with more leads, people would need sort of more patches around their body to be able to collect multiple perspectives.
So I suppose it's a cardiologist that's the appropriate specialist, from at least as a human being specialist, to look at this data. Do you have a sense of what a cardiologist looks at? Is it just they're, taking things in with their eyes and making an expert opinion, or is there some process or tool they use to help explore the results of these machines?
When we started this project, one of the first things we did was we went and read a couple of cardiology textbooks to understand exactly how a cardiologist would go about trying to make these diagnoses. There are patterns that cardiologists look for. Looking at the structure of an ECG signal, there's like a small wave that corresponds to the atria contracting and a larger wave that corresponds to the ventricles contracting, and that's the that's the double beat you hear of the heart when you're listening to it. There are patterns within one beat and between beats that are important to make differential sort of diagnoses on whether this patient has arrhythmia A or B or is normal.
It sounds, if I understand correctly, that something about the relationship between those, that beat and the call and response, if you will, of the heart is what's critical. Is there also anything tying it beat to beat? Are there intervals between beats or patterns and irregularities that can come out there as well?
Yeah, so there are a lot of things. First thing one would look at is the rate of the heart. So is the heart going really fast or really slow? That's not important by itself because it's not considered an arrhythmia that if it's just a fast heart rate or a slow heart rate, but it is useful when we also look at other features of the ECG. So for example, to diagnose a heart block, one would see if a small wave is followed by a large wave, what we call the P wave and the QRS complex. And if this relationship between the two is not consistent, then we know that there is a possibility of a block here or some other arrhythmia.
So what are you trying to predict when you built the model?
So we're doing end-to-end mapping from the ECG signal to arrhythmia annotations, which means that in a time period, if a patient exhibited one arrhythmia for the first 10 seconds and another arrhythmia for the next 10 seconds, then we'd be able to say so.
So it's not just, my first observation here is that it's not just a binary classifier. That would still be useful. Does the heart have a problem or not? But this is better than that. You're actually doing classification into several types, but also, if I understand correctly, you're doing it at each interval, so you potentially observe different classes at different periods of time. Is that correct?
That's right. So we're able to do diagnosis of up to 13 arrhythmias and also noise and the normal sinus rhythm. And we're able to also do, as you said, sequence annotations. So even within 30 seconds, if a person switches the type of rhythm of the heart, then we can identify that.
And why 13? Is that the breadth of all possible ailments and issues you might be able to uncover?
13 is actually a pretty large number considering previous work. So previously, when people tackled arrhythmia detection, doing it across a wide range of classes requires a lot of data. And that's not something that's easily acquired or even easily labeled because one needs cardiologists or experts to be able to do this. Doing it across a wide range of arrhythmias is very new. And with 13, we cover heart blocks, we cover atrial fibrillation, ventricular tachycardia. So it's covering a wide range of different arrhythmias. In terms of adding more arrhythmias, it's definitely possible to add a few, especially if we have multiple leads.
In some sense, the project you're working on is a time series project. These are measurements that are a time series, and there are a lot of historical techniques we've used to solve some problems like that. Why have the sort of traditional methods not made this a solved problem yet?
So previously, people, when tackling this problem, used to look at wavelet approaches. The traditional approach was to do some kind of feature engineering, take a discrete wavelet transform and take a continuous wavelet transform. But the problem with this is that a different wavelet is required for different rhythms. So there are no wavelet transformations that work consistently well across different rhythms. So a lot of hand engineering going on here. And that's a story we've seen in a lot of signal processing and in image processing, where deep learning is able to do better than where feature engineering used to play an important role.
Having had a chance to read the paper, I now know that you guys made great progress using deep learning. I wanted to ask if that was something you knew from the onset. Were you deep learning researchers looking for a good domain, or were you interested in arrhythmias and identified deep learning as the obvious solution?
Our lab focuses on applying machine learning to healthcare. I think it's an exciting space. Because we have a lot of data that we didn't previously have before. And we know that machine learning models based on deep neural networks have been able to consistently approach and exceed human performance rates when large annotated data sets are available. And we've seen this in a lot of image recognition, in speech recognition, and increasingly in medical imaging.
So I'm curious about how much natural variance you see across patient in the data set. I could see presumably left-handed and right-handed people have identical ECG data, but maybe age or more important factors like being a smoker or a long-distance runner could impact it. How much variance exists between patients?
The short answer to that is that I don't know. The idea behind having this deep learning model is that you're able to do it consistently well across a wide range of patients. So while feeding data into the network, we do not give any context of what the patient history is, of previous arrhythmias or medications that the patient might be on, but just focus on the task of, given this ECG, what is the arrhythmia that is exhibited here, and can we identify that with high accuracy? We use training and validation sets. So we're able to see whether we're able to generalize well across patients. We are able to do that here, as we see on the validation sets and on the test sets.
And how big of a data set were you able to work on?
We are working with a data set that's 500 times larger than other data sets of its kind. The MIT BIH data set consisted of 47 patients, and here we're working with a data set of 30,000 unique patients who have worn this Zio patch that we're collecting data from.
Tell me a little bit more about that patch. Is it something your lab developed, or is it a common tool available in industry?
Yes, we worked in collaboration with iRhythm, which is a company that has developed this patch that goes on people's chests and continuously monitors their heart signal for up to 2 weeks.
And does that end up being noisy? Or, I'm curious, it seems like it's external, it's non-invasive. There must be a certain amount of noise. Can you speak to that, maybe how it impacts the training of the network?
Yeah, so there is noise. We have a whole rhythm just dedicated to noise. So after all of these raw signals are collected from patients, expert clinicians are annotating them, marking the start and end of every arrhythmia that is exhibited, and also classifying noise. If, like, a patient might drop their patch on the ground, that segment of data would be classified as noise by the expert clinician. And then we take these expert annotations and we feed them into the neural network. Of course, they have some noise, but we hope that there is more signal than noise so that the network can learn to smooth over the noise.
So it sounds like your ground truth comes from those expert clinicians. Can you talk a little bit about that process? Are you using any consensus or anything to double check that there aren't human errors introduced to that step?
So we have a training set and we have a test set, and we have different strategies for both. So in the training set, we don't care too much about whether what we have as a label is definitely correct. We just want a good ground truth. But for the test set, what is important is to have a ground truth that is very solid. And for the test set, we have a group of 3 cardiologists sitting in a room and coming to consensus of what the right labels for this ECG record. And we do this for 336 records from about 300 patients. And along with the 3 cardiologists who provide the ground truth, we also have individual cardiologists who are not part of the committee also go and label the data so we can compare the performance of individual cardiologists to the performance of our model.
Interesting. So let's get into that. Tell me a bit about how the human experts fared and how your model did in comparison.
We are able to beat the performance of individual cardiologists on the test set that we have across a wide range of arrhythmias. This is a big deal because, unlike cardiologists, models can run on data all of the time. And this is increasingly important with the bringing of life to continuously monitor devices on the market, because suddenly we have all of these heart patients monitoring their heart conditions 24/7 for many weeks, and it's just impossible for a cardiologist to go through all of this data. The reason patients go through continuous monitoring is because, let's say I have an arrhythmia, and I know that from the way my chest feels, that it just comes up at some points of the day, and then I go into the hospital to see what might be wrong. But during my visit to the hospital, nothing wrong shows up. As soon as I leave the hospital, suddenly I feel it again. We know that with continuous monitoring, we can find a lot of things that we wouldn't have been able to find just from a short visit to the hospital. And this is where I think the model being able to do as well or better than a cardiologist is really useful.
Yeah, beating their results obviously has advantages in that maybe it's the primary diagnostic tool. I hadn't yet thought of some of those implementations you'd mentioned, that this could be a continuous out-of-care monitoring system as well. Do you see that as the ultimate end? Is it going to go to being part of a system that people who are, under observation and whatnot have in their homes? Or do you think it could even go so far that the average person has a home test kit and every so often they're taking diagnostics that get uploaded to their doctor for review or even are reviewed immediately?
Yeah, I definitely see that as an important use case. Another one is, let's say I do not have access to a cardiologist where I live, or my cardiologist appointment is months away. Is there any way I can take action about what's going on or understand what's going on any sooner? This is a great way of being able to do so. Is just stick a patch and then being able to find out what's wrong. Of course, there's some legal barriers to this, but I think as the field becomes more welcoming to these sort of things, we'll make progress on that.
So I asked this next question mostly in jest, but I'm curious to see how you respond to it. Let me describe a scenario to you today. Tell me if this sounds like your career or someone you work with. You're the data guy. People come to you when they need numbers and reports and stuff pulled out of the database. You're good at your job, and you're almost a victim of your own success because people know you're reliable. As a result, you're often inundated with tons of requests from all sorts of different directions. While being helpful, sometimes you never get your actual work done. If you're with me so far, let me take it a step further. I bet at least once you've worked with somebody who was maybe a little difficult, a little demanding, somebody whose job it was to get the numbers right, and they were in, for whatever reason, a difficult spot trying to put a positive slant on a negative message. As a result, they're trying to slice and dice this data in a million different directions. That feels aimless for you and a slow, inefficient process. You could close the gap on that situation almost immediately with Periscope Data. Not only can you quickly query your database and visualize the results, not only can you make dashboards out of all the interesting visualizations that help tell your story, but on top of that, you can really build in these great automated ways of changing the filtering on the dashboard. So anticipate all the follow-up requests. Are people going to ask you to slice the data by marketing source, certain date ranges, who knows? Program all those things easily in advance. Let the users configure what they want to look at and visualize to their heart's content. All the while, they're just relying on the queries that you checked and you know are reliable, so they're getting good data. Make that dream happen at your organization using Periscope Data. Check them out at periscopedata.com/skeptics. One more time, that's periscopedata.com/skeptics. So I asked this next question mostly in jest, but I'm curious to see how you respond to it. Are you worried that your work is going to put all the cardiologists out of a job?
So I've spoken with quite a few doctors about this work, and they seem very excited about it, about AI being applied to cardiology and more generally to medicine. It's not an immediate threat to doctors. It's not a threat to doctors at all, as much as it is a way for them to focus on more important activities. There's this famous painting called The Doctor, which I learned about recently, where there's a kid in the center of the painting, and sitting right to the kid, leaning intently, watching the kid, is a doctor, and in the corner are the child's parents, and is supposed to characterize the doctor-patient relationship that is respected. But what we often see is with something like ECG interpretation, the doctor is going to be looking at a screen trying to find out what's going on here rather than trying to communicate with the patient of what strategies can be taken moving forward to make the patient feel better.
Oh, that's an excellent point. I've heard, it's not really my field, but I hear a lot of science news stories that say that, studies are seeming to imply that bedside manner and patient care like that is critically important, but often overlooked. So I think that's one of the best examples for how automation it actually optimizes all ends of the process, in my opinion. Well, I'd like to go back and talk a little bit more about the model in some detail. You had mentioned that, as far as we know, the data set you had to work on is the largest of any previously studied. How important do you think the size of that data contributed to your results versus the neural network you chose to implement?
It's definitely important what the size of the data set is. It's also equally important that we have a model that is able to exploit all of the available data to make better predictions. So one of the beautiful things about deep learning is that if you look at a graph of amount of data available versus performance, then you see that as the amount of data increases, the performance of a model keeps going higher and higher. And this is not something we used to see with models before deep learning came along, where as the data size grew, we used to see the models plateau out. But this is not the case with deep learning. So the fact that we have a lot of data means that we can employ really big models to be able to fit all of that data and make better predictions. So here we're working with a 34-layer deep neural network that we developed that runs 1D convolutions over the ECG signal. And 34-layer neural networks are pretty hard to train. So we employ some tricks that people have used to achieve the best scores on image recognition tasks into our domain, into our network, to be able to train such a large network.
Oh, tell me a little bit about those tricks.
One thing that we find while trying to train really deep networks is as we increase the number of layers in the network, they become increasingly hard to train. And how this exhibits itself is that the training error is higher for larger networks. But this doesn't make much sense because one can imagine if one has a network that's 20 layers as opposed to one that's 10 layers, then one should just be able to set the first 10 layers to just learn the identity mapping, basically do nothing, and the next 10 layers to do what the network of 10 layers was doing. So in theory, it should have a richer solution space. Few ideas that we employ is shortcut connections with residual units, and that's something we saw win the ImageNet competition a couple years back. We also employ a few other optimization tricks to make optimization of the network easier. One trick to optimize is simply knowing how to set up the order of the layers in the residual units. There was some work that figured out which way to order batch normalization with ReLU nonlinearity and the weights so that it allows information to propagate the best down the network and the gradients to flow back easiest.
So essentially am I correct in saying that's a technique for helping avoid the vanishing gradient?
So it is a technique that allows for direct information propagation from the input to the output.
I gotcha. Okay. Yeah, that leads to another question I wanted to ask. I was a little bit surprised, not that, I'm an expert in this area, I'm not, but I was surprised you were using convolutional neural networks when my brain immediately went to recurrent neural networks, because I see the ECG data and I see, something that's sequential in nature. Could you talk a little bit about that choice and maybe are the shortcut connections sort of giving us a bridge between a CNN architecture and an RNN architecture?
Yeah, so I wouldn't be surprised if it's possible to arrive at a very similar performance with a recurrent neural network. The higher level goal of this is to be able to do better than human performance. Whatever it takes to bridge that gap is what is guiding our process in terms of how we design the network. And as soon as we've passed human performance, we've achieved our goal, so we can stop trying to look at ways to change the network. That being said, the idea of using convolutional neural networks to signal data is not all that new. In fact, as far back as 1989, the one-dimensional version of convolutional networks called time delay neural networks were applied to the task of phoneme recognition. So one advantage that we have while using a convolutional neural network architecture rather than a recurrent architecture is that we can train networks faster. And this has enormous implications in simply being able to guide our design choices as I'm trying to make the network better, is that instead of having to wait a day with a recurrent neural network, I have to wait an hour with a convolutional neural network. And that gives me a big jump in being able to iterate quickly.
Oh, yeah, great point. So you also make another interesting point that you guys achieved your goal. You exceeded human performance. So immediately we have a very usable tool. There's some limit too, of course, that this is a non-invasive measurement device, so it can't have a perfect accuracy. But do you think there's room here between where you guys are and maybe a further accuracy, or are you at or near the limits of what's capable given the precision of the device?
So I think we're close to the limit given the scope of the arrhythmias we are looking at and the device we have. If we look at the mistakes that we make, it's very unclear whether the group of cardiologists is correct or we are correct.
Mm-hmm.
So one thing that would inform whether we have reached the maximum possible performance is to do a agreement study between groups of cardiologists. But cardiologist time is valuable, and so doing that experiment is costly. And that's not something we have done yet. But I think in terms of the more important goal is to exceed the performance of one cardiologist, because in the clinical setting, it is one cardiologist who is taking a look at a patient's ECG readings, not a group.
So it seems you guys, like you said, you've achieved that goal. The paper shows the empirical results from the test. It seems like there should now be efforts towards getting your system rapidly deployed to doctors and hospitals as a diagnostic tool, maybe even to patients in the field. Is there anything that makes this a special case or requires more study before that step takes place?
So we have developed this in collaboration with iRhythm, who already has a workflow in place to go from people's recordings to reports that cardiologists use in being able to make their clinical recommendations. And so we're focused on getting this into that workflow as soon as possible. And iRhythm is, of course, also excited about that. And so this will soon become a part of the way we're doing diagnosis of people's arrhythmias.
That's very exciting. I'm curious if you could comment then on the sort of end-to-end use case here. When did research begin and when do you think devices, this might be deployed in the field? I'm really curious about that cycle of how long it takes innovation to hit in the medical world.
We've been working at a fast pace in getting this from an idea to a stage at which we have a research impact. So we started this project late last year in the fall. Just before the summer, we released a paper. So we've gone from idea to research impact within a year. And hopefully in the next few months, we can go from research impact to impact straight in the hands of the patient. I also think another important contribution is being able to put out there that doing such a thing is possible, because it is now possible for other people to use this work to be able to perform the diagnosis of arrhythmias. Yeah, it doesn't take too much to record one's own ECG. I've seen tutorials online of putting electrodes on either side of their chest and being able to see their ECG. So it's definitely something that's doable.
In terms of what makes this problem hard, can you comment a little bit more detail on that? And if this is a bellwether for what's to come, whether are there similar hard problems that we might work on?
One of the challenges is that it's difficult to diagnose with a single lead ECG what is easier to diagnose with 12 lead ECGs. Another challenge is that the difference between heart rhythms are often very subtle. So in the ECG morphology, as I said earlier, there's a small wave, which corresponds to the atrial contraction, which we call the P wave, and a sort of larger up and down you see on the record, which corresponds to the ventricles contracting. The normal rhythm is characterized by a few rules, like it should be between 60 to 100 beats per minute, and there should be one small wave before every large wave, and then the large wave, the QRS complex, should be narrow. But one arrhythmia that we look at is ectopic atrial rhythm, and the way this is characterized is the P wave is a little different. It's either low voltage, so you don't see it as clearly, or it's inverted. And this is a very subtle difference. So the ectopic atrial rhythm and the sinus rhythm are easy to confuse. And sometimes this confusion doesn't matter. So ectopic atrial rhythm is not usually treated. It's considered a benign arrhythmia, but sometimes it's serious. So if the heart rate is less than 100 beats per minute, it's called ectopic atrial rhythm. If it's greater, it's called supraventricular tachycardia, also known as SVT. And SVT is treated unlike EAR. If the patient has symptoms, if it's in the acute case, the patient is asked to gag or hold their breath. In the chronic case, they're given medicines or a surgery called catheter ablation is performed. So that's another piece of what makes this problem interesting and challenging.
You had mentioned going out and reading a lot of the cardiology literature to get started. How much effort do you think projects like yours and future ones with applications like this, do we need to have people studying machine learning and a domain, or how much domain knowledge is really required to get going?
So I think it's important to really understand domains well. It's very easy to have a giant hammer and think everything is a nail. And I do think deep learning is really powerful. But I also think as machine learning researchers, we need to go out and find problems where we can have most impact. And part of that process is to really go deep into other domains and try to understand what the problems are, or even talk to experts and know what the problems are. And to arrive at an understanding of where machine learning can be applied to a lot of problems outside just pure machine learning, I think it's important for different domains to come together. That is either possible when people from other domains get an understanding of machine learning to know what's possible and how they can change things in their field with machine learning. But the other side's us as machine learning researchers going out there and seeing what problems in other domains could be solved with a machine learning toolkit.
Definitely agree. What's next for you in your career and research, and also this project specifically?
So my work is in applying machine learning to healthcare and medicine. Some of my effort recently is towards identifying what the high impact problems are in a variety of subfields and how they can be tackled with machine learning. As far as this project goes, I'm really excited about seeing it being used and applied to real patient data out in the world. So that's something I continue to work towards.
Pranav, I want to really thank you for coming on the show and for doing this work. I think it's really promising stuff. I love seeing results like this coming out of the machine learning community. It seems like we're really in a transformative time for healthcare.
Yeah, definitely. Thanks for having me, Kyle. This has been great.
Data Skeptic is a listener-supported program. To support the show, visit dataskeptic.com and click on the membership tab.